Hello everybody and welcome. So in this video I want to demonstrate the general idea of the central limit theorem. And what the central limit theorem says is that regardless of the distribution you start with, so you have some random variable x that has some distribution, the idea is that if you take large enough samples from that distribution, the sampling distribution of the sample means will be normally distributed, and the mean of that normal distribution will be the same as the mean of the random variable, and the variance of that normal distribution will be equal to the variance of your original distribution divided by the sample size. Okay, so what I've done is I've constructed just sort of what I'm calling this wacky distribution here. And the reason I made it wacky is to illustrate the point that it doesn't matter what distribution you start with. So this is a discrete probability distribution. It takes on the values 1, 7, 12, and 28 with probabilities 0.3, 0.2, 0.4, and 0.1. Okay, so let's start off by just getting an idea of what this thing looks like. So in this line of code right here, what I've done is I've created a random vector. The length of it is going to be 100. And what I've done is I've sampled from the sample space as I specified on the other page, 1, 7, 12, and 28, with the probabilities that I've specified. Okay, so what we're going to do is we're just going to copy this guy. We're going to go into our R console and paste him in. Okay, so hopefully this has created the vector. And I want to just take a look at the first 10 of these. We don't need to see all 100 elements of this vector, but I use this code to just get a look at what I'm dealing with here. So it's going to be something like this, but it's 100 long. Okay, very well. Okay. The next thing I want to do is I'm going to create a function that allows me to look at the theoretical expected value for any discrete random variable, and in particular I'm going to use it for the one that I've just created. Okay, so the expected value is going to be a function of two vectors x and y. As we know from our math stats class, the expected value, maybe I'll just write this down here, the expected value of x for a discrete distribution is just equal to the sum of xp of x over your sample space. Okay. Well, this looks like a dot product to me, a sum of a bunch of things multiplied together, and in fact, that's exactly what it is. So for our R code here, yes, I'm creating this function of two vectors, and the output of that is just going to be the dot product of the two vectors. So I'm going to take this function, and I'm going to drop it into R. R liked it. There's no debugging, at least ostensibly, that needs to be done there. And then my vectors x and y are just going to be the sample space and the probabilities that I've specified. Okay, and let's see if our function works. To test it, just going to print the function on x and y, and we get 9.3. Okay, so that's the theoretical expected value. Let's see what the mean was of our vector. Oh, I guess I'm going to have to remake it. I'm going to call it something else just because I want to leave x and y as our pet distribution here. So let's just call this z. Okay. The mean of z, and this is this is the actual sample mean of this sample of 100 from this distribution, is 9.87. Let's do it again and see what we get. And again, and see what we get. So we're getting things that seem to be reasonably close to the theoretical expected value. And it's actually the distribution of these guys that we're going to be looking at in more detail. But first, we're just going to move on with the tutorial here. Okay, I want to create a function that allows me to look at the theoretical variance for a discrete random variable. Okay, so first let me just refresh everyone on this. What's up with the variance? The variance is the expected value of x minus mu squared. So, if the mean was 0, then it would just be the expected value of x squared. It's the second central moment, or in the way we're computing it here, it's the second moment about the mean of this distribution of this random variable x. Okay, so from this, I'm sure you guys have seen this a million times, you can get to this nice computational formula for the variance simply by FOILing out what you have in here, distributing the expected value, noticing that the expected value of x is actually the same thing as mu, and so we add minus 2 mu x squared plus mu x squared, we get minus mu x squared, and then this is our result that we're going to use to make the code to make a function to give us the variance of any discrete random variable. Okay, so we pop into our editor here and we look at what I've done. So I'm making a function. It's going to eat two vectors, the sample space once again and the probabilities. Okay, I'm going to define this output vector in advance because we're going to be doing something with our x, and namely squaring it. So for each term in our sample space, we're going to take that value and square it. Okay, so for I and 1 to the length of x, because we want to run this loop through the vector, our output vector indexed at I is just going to be equal to our original vector squared. Okay, so this gives us now a vector of each element in x squared. And then the variance that we're after is just going to be now the expected value of this new vector, x squared, along with the original probabilities, minus the original expected value of our random variable, all squared. Okay, where could this potentially get a little bit confusing? Okay, I guess I should add that this piece, expected value of x squared, is now equal to the sum of x squared dx. So it's the dot product of our squared vector with the probabilities. Sorry if I didn't make that clear. Okay, so we've got all of this good stuff. We're going to copy from our editor, and we're going to paste into our console. Okay, and let's see what our variance is for this random variable that we're playing around with, our wacky distribution. Okay, it's this thing. And let's see what the variance of our sample. Okay, so it's something close, which means that this is plausibly the theoretical variance. Okay, let's move on because we don't want this video to go on forever. Oh, I may have done this before I made these functions, but anyway, we want to look. Let's just take a look at our distribution and see how crazy it is. So in this code, what I'm doing is I'm creating a histogram of our sample from our sample space with the probabilities specified. Replace is true because we're going to do it 10,000 times. We need to have something there to draw from. Okay, and we're hoping that by doing it 10,000 times, we're going to get a reasonably accurate picture of what's going on with the distribution. There are other ways to do this in R other than actually doing a simulation. You can actually, take you can create a discrete random variable and see exactly what it is. But for our purposes here, we're just going to do it this way. And this is our thing. So we can see that this is decidedly not a normal distribution. Very well. Okay, so the claim of the central limit theorem is that if we take a sufficiently large sample, they usually say n's got to be more than 30, or as like a lower, as sort of like, you'd imagine that the wackier, the less normal the distribution is, the more having a large sample size helps to like diffuse that. So, you know, this is just sort of like the suggested minimum sample size that will guarantee that the sampling distribution of the sample means will be normal regardless of the distribution you're drawing from. Okay, anyway, the claim of the central limit theorem is that if we take sufficiently large samples, then the sampling distribution of the sample mean will be normal, with the mean of that distribution equal to the expected value of the random variable, and the variance should be equal to the variance of the random variable divided by the sample size. Okay, so we want to test this claim, so we're going to construct a function, and in our function we're going to draw 10,000 samples. We're going to allow ourselves to specify the sample size, which will be good for testing this n equals 30 business. And then we're also inputting into our function what I'm calling the constituents of this random variable, which is just the two vectors that we've been dealing with, namely a vector that represents the sample space or the possible outcomes and their associated probabilities. Alright, so I'm calling my function CLT, or central limit theorem test. It's going to be a function of the variables that I just specified. I create my output vector, which is going to be from 1 to 10,000. So this is basically just a placeholder vector because I'm going to be getting 10,000 sample means and I need somewhere to put them. Okay? I create my loop for I in 1 to 10,000. Output indexed at I is just going to be the mean of a sample that conforms to what I've specified. So we get in the sample function in R, you put in what you want it drawing from, which is going to be our sample space. The size is going to be the size that we specified up here. Replacing, obviously, needs to be true, and the probability of drawing what we draw is specified by our vector of probabilities. Okay, and then for the output of this function, to get everything in one place, sorry if this code is kind of messy and confusing, but what we're going to do is we're going to create a histogram of our output. So this is a histogram of the 10,000 sample means. And okay, in like the main title for this graphic, I want to get like the mean of the random variable itself, which is our expected value function. Okay. And I want to look at the variance of the random variable, which is our variance function on the sample space and probabilities we've specified. So that's like the theoretical thing that we're after, or for our random variable. And then in our subtitle, I'm giving you the mean of the sample means. Okay, so I just take the mean of the output vector, and I've decided to do some rounding so that it doesn't get ridiculous to look at. And then we're also going to see the variance of the sample means. So what we want is for this guy to be equal to the variance of the random variable divided by whatever our sample size is. Okay, so I'm going to put this code into R, into the console here. Okay, let's make sure X and Y are still what we want them to be. Okay, that's our sample space. Okay, those are our probabilities. So now I'm going to call the function I just created, central limit theorem test. And the size, we're going to do 100. Nice big N, so this should really be normal. Sample space and probabilities. And what do we get? We get this thing, and our histogram, in fact, does look approximately normal. the mean of the sample means is in fact very close to the theoretical mean of the random variable. And the variance of our sample means is in fact very close to the variance of the random variable divided by 10, 100. Okay, so that gave us exactly what we wanted. Let's do it again to make sure it wasn't a fluke. Yep, this one's even closer. The variance is a little bit off, but I mean it's still very close, and it's plausible that this is our theoretical assessment of what should be happening is probably still happening. Okay, and then just for fun, let's take a look at what happens if we had had a much smaller sample, like less than 30. Let's say our sample was only 4 things. Our sample size was 4. We look at this, and I mean, it's not like disgustingly non-normal, but it is, I wouldn't look at that and say that that's obviously has to be a normal distribution, whereas I was much happier doing so for the larger sample. Let's do an even smaller sample size. Okay, and then this thing is looking really pretty hideous, and in fact, it's clearly not as normal as we would like. Okay, thank you all very much for tuning in. I hope this was helpful to someone. Yep, have a good day.